Here is part 2 of the standard potential and free energy. Use the data from the reference sheet to calculate the standard cell potential, standard free energy change, and equilibrium constant for the following reaction at 25 degrees Celsius. Comment on the spontaneity of the forward reaction and the composition of an equilibrium mixture of reactant and products. So it's asking for quite a bit of things, and I'm going to take one step at a time, one question at a time to solve this particular problem. So let's calculate the very first one, which is the standard cell potential. So that I'm looking at this one right here. The standard cell potential is your E sub naught. And so we're going to look at the oxidation process of this equation over here. So the oxidation and reduction half reaction is as follows. So oxidation and reduction on the bottom. Oxidation is where iron solid forms into iron 2 plus aqueous. The oxidation number for iron solid is 0, and for Fe2 plus, it's 2 plus. So how many electrons did you need to add? It needed to add 2 electrons on the right-hand side to let you know that, hey, 2 electrons needed to be taken out in order for the oxidation to go from 0 to plus 2. In the reduction side, we're dealing with silver. So Ag plus aqueous forming into Ag solid. Notice that it is 2. Okay, you will see the coefficient 2, so I'm going to add that 2 right here. The oxidation number for silver is +1, and for silver solid is 0. So you only need 1 electron in order for it to go from +1 to 0. So 1 electron. However, it is accounting for 2 silver, so I will have to add 2 electrons. And if you want to think about it, you think about it as having +2 here and a 0 here. Now that we know the oxidation and the reduction process half reaction for this whole redox reaction, we can find the delta E for each of these guys. Delta E naught or the standard cell potential for each of the reduction and oxidation process, you're going to look at the reference sheet. So in this reference sheet shows all of the reduction process. And we want to make sure that one of them actually is an oxidation process for iron. So if you look at iron over here, iron 2 plus 2 electron forming iron solid. Well, in our scenario, it's the other way around where the iron comes first, the solid comes first, then forming into iron 2 plus and 2 electrons. In the reduction, if this was reduction, it's negative 0.44 volts. However, if we were to go to the other way around, if it's an oxidation process, it's the opposite value. So the cell standard potential for iron in an oxidation process would be positive 0.44. Now let's look at silver. Silver was the other one. That's this one, and it's already in a reduced form in our half reaction. So therefore, this is 0.80. So we take that 0.80. Let's go back to our slide. In our side, here is my oxidation process for iron, and we said that that was going to be plus 0.44, 0.44 volts. Whereas silver, it was 0.80 volts. Now, go ahead and add these two values together, and you should get 1.24 volts. So my standard cell potential for this reaction is 1.24. So that's my first answer. Second one, now I want to know the standard free energy change. Standard free energy change is asking for delta G naught. The equation for delta G naught in a standard potential and with the standard condition, it would be delta G naught is equal to negative NF E naught. So N represents the number of electrons being transferred, F represents the Faraday's constant, and E represents the cell. So let's go ahead and look at N. And N, as you can see, there's 2 electrons being transferred. So we're going to go ahead and write -2 electrons. The Faraday constant is something that you should just memorize or have it in your reference sheet. 96485, and it's Coulomb per mole dot E. And my potential for E, okay, my standard cell potential is 1.24. Now I could write volts, but volts is also known as joules per coulomb. And go ahead and cancel the coulombs out. I'm going to cancel the E, the electrons out, so I'll be left with joules per mole. So if you were to calculate, try calculating this out and come back. Now this is what your calculator probably has spat out, and I'm going to put this in 3 significant figures, and that would be -2.39 times 10 to the 5 joules per mole. Okay, so that's my delta G naught. And now it wants to know what is the equilibrium constant. That's asking for K. If you want to know K, then you will need to utilize this equation where delta G naught is equal to the negative RT ln of K. We know R, that's the gas constant. Temperature we know, well, it's in Celsius, but we could definitely change it into Kelvin. We know delta G naught because that's what we calculated from above, and then we just need to find K. So what I'm going to do is actually divide this by negative RT, both sides, so that you would just get ln of K is equal to all of this guy. So if I were to plug in the value, -2.39 times 10 to the 5th power, that's joules per mole, all over, R would be 8.314. Oh, I should put negative 8.314 joules per mole per dot K. Per mole per dot K. And then temperature, it's in 25 degrees, but if you were to take this temperature 25 degrees into Celsius, into Kelvin, it would be 298.15 K. So 298.15 K. So I'll go ahead and punch this out into the calculator. Here I go. So I have -2.39 times 10 to the 5th power. Okay. And that is I'm just going to press enter. Divide that by the -8.314 times it by 298.15, and I'm going to close the parentheses to let you know that, to let the calculator know that everything is under that. So I get 96.41. Okay, 96.41 approximately. 1 is equal to not K, but ln of K. And to get rid of ln of K, we take e's of it, and e's will get rid of ln of K, and that will be left with K. So let's go back to that calculator. And we take second ln will give you E, okay? And then now we plug in the value before. I'm going to just put second answer to show you that I'm going to put in all of these values in here. That gives me 7.46996 and so on and so forth to 10 to the 41 power. And so I'm going to go ahead and put this in 3 sig figs, which is 7.47 times 10 to the 41. This E is 10 to the, okay? 7.47 times 10 to the 41 power, and that would be my K. So with this large K, okay, what does this tell me? It really tells me the composition of the equilibrium mixture, showing that the product, there's a much more product than reactant. Kind of went into completion if you think about it. What about the spontaneity? Well, we can tell by the clues of two things. The delta G for this guy, right? This is delta G naught. It's a negative value. So if it's a negative value, what does that tell me? Well, it tells me that this is a spontaneous process. E naught is a positive value, and that also tells me that it's going to be a spontaneous process. The K, well, really doesn't really tell me that it's a spontaneous process, but it really does tell me that the equilibrium mixture of reactant and product, that the product, there's a lot of it compared to the reactant at equilibrium.